Today, I think most of topics are covered by other presenters. We are going to talk about how to plot those green plot for relaxation dynamics and distribution of charge carriers in the space. So overall, the purpose of the implementing these non-adiabatic couplings, at least in my project, was to explore the charge transfer at the interface of a conjugated polymer and acceptor unit. Usually, this blend will be used in the solar cell applications. So this method can be used to actually quantify their photovoltaic performance. And usually, the system will be actually excited with the promotion of the charge carrier and based on the oscillator strengths, and then we will track the electronic relaxation, the rates, and also charge transfer. So, and this plot will be the conclusion of this method and this presentation, and we will review them at the end. So, I want to a little more focus on the technical details, codes, and the needed files that we need to have those plots. So just as a review, we started with geometry optimization, heating, molecular dynamics, coupling calculation, and last week we review how to generate RR file, the elements of the Redfield tensor. Also, to finish the today calculation, we need to start again from geometry optimization. We need to calculate partial charges and calculate the band out file out of the partial charges. And at the end of this process, we will have energy pop for master optics and band out file. And together with RRR file, we will have the all input files needed to have those green plots. So the most important point before starting is that the range of the orbitals that you choose should be the same. Actually, that included the energy pop, but we should use the exact range for the coupling calculation and also doing the partial charges to generate the needed input files. So so we already have RRR, and to have the master optics and band out file, again, we need to have the concar file out of geometry optimization and use this incar file in the bin directory. And after running that, we will have those for master optics and band outs. This is the incar file needed to generate the partial charges, so you just need to specify the range of the energy of the orbitals. Usually you can find them easily in the energy pop. After running that simulation and finishing the jobs, you need to run this Perl script. So here again, you need to just the only things that you need to adjust in this script is to give it the range of the orbitals that you need. Again, exactly should be the same, the range of the energy pop. And at the end of this process, you will have the band out file. Also, running this 3 steps will give you the 4 master EQ that you can copy it and save it as 4 master optic. So again, before doing the calculation, make sure that check the size of the input files. So energy pop for master optics and band out. So this first number of this should be the same. Actually, is equal to the number of orbitals that you perform the coupling calculations. So we have 4 input file here for master optics, band out, energy pop, and RRR. And now we can perform this MATLAB code. I just a little tweak that and add name to it, summer 2022, but you can also use the original file. So in this file, I a little change it. So the only thing that you need to specify is the initial transition, cell size in the Z direction, and also number of time steps that you perform in your simulation. And so the initial transition will be based on the oscillator strengths, which give you the highest probability of the excitation for that transition. For instance, here for today's result, we can see the transition from HOMO -3 to LUMO +2, which is the second highest oscillator strength value. But usually you should repeat that for multiple oscillator strengths. After running the MATLAB code, it will give you some numeric value as KE and KH, which are relaxation rate of the electron and holes. In previous presentation, we reviewed them. And this two panel will be the outcome of this section. So first, an electron is promoted from HOMO to LUMO. System is excited based on this initial transition, and as time goes, we can see that the electron, the yellow color, cascade down on the LUMO orbital. Sorry, this is a typo. It should be a LUMO, and also this hole will stand on the HOMO. And also here we can see that the distribution, a special distribution of the charge carrier in the z direction of the cell size. You can see that at the end of the simulation, electrons will relax relax on the acceptor unit and holes on the backbone of the conjugated polymer. Also, another interesting outcome of this kind of calculation will be quantifying the charge carrier. So from difference of the expected value of the charge, actually electron and holes, we can have the dipole. The definition is presented here. And by definition also, the slope of the dipole moment over time will give you the current density. So here we use this equation and this results to quantify the current density. So the system that give you the highest current density usually is expected to have a better photovoltaic performance. And yeah, I would be happy to answer your question, if any.
Okay, pues yo me